Dear all, I hope you are doing well in this unpleasant situation we are suffering all around the world. My name is Raúl Suarez. I'm from the Institute of Industrial and Control Engineering at Universitat Politècnica de Catalunya in Barcelona, Spain. And today I will talk about graph synthesis of articulated objects with n links. Let me start talking about the two typical types of deformable objects. These are elastics and plastic one, depending on whether the object can recover the original shape after deformation. We will deal with a different type of deformable objects, which are the articulated objects. These are composed by solid segments linked by joints. The links are not deformable, but the object as a whole can change the shape, and therefore is another type of deformable object. The joints in turn can act as elastic, plastic, or even free joints. This is the case we will consider in this work. Here you can see some example of deformable objects, articulated objects, so they can change the shape even when they are composed by solid links. So the problem we will address is that given a serial articulated object with n links, search for a set of contact points on the links that allow a foreclosure grasp. By foreclosure grasp, we understand that the grasp will constrain the object, and so it cannot be moved either in the absolute reference frame or move each of the joints in order to change the shape of the object. I want to remark that hand reachability is not considered, so the solution we find may be not reachable by a particular hand. Let me now give a few words about the number of required contacts to immobilize an articulated object. So previous works have shown that an articulated object composed of n polyhedra with 1 degree of freedom rotational hinges and using frictionless contacts requires 2n plus 5 contacts for arbitrary polyhedra. So this means that the shape of each link is arbitrary. And in case that the polyhedra satisfy some constraints, and also the way in which they are linked with each other also satisfies some constraint, this number can be reduced to n plus 6. I want to remark that frictionless contacts allow forces with only one independent component, so which is the normal direction to the surface, which are being in touch with the finger. Of course, this condition could be modified for frictional contacts, because frictional contacts allow the application of contact forces with 3 independent components, and therefore the minimum number of contacts is even reduced, theoretically by 3, due to the friction influence. So it is typical to approximate the friction cone by a polyhedral convex cone with a determined or predefined number of edges. Equivalent condition can also be determined for 2D change. These are planar change with polygons instead of polyhedra. And also for other type of change and specific cases like change with joints with more than 1 degree of freedom, or closed kinematic change, or any other variation you can imagine. So I will remind the condition for a foreclosure grasp, that is, the convex hull of the applied wrenches on the object must contain the origin of the wrench space. And this is very well known for solid objects. So in this way, the applied wrenches can span the whole space, and therefore a combination of these wrenches can generate any wrench that can counterbalance any perturbation. And for the general case, then the number of applied wrenches or independent wrench component, if we are working with friction, must be larger than the number of degree of freedom. There are some particular exceptions, but we will not enter in this now. So let's go now to the graph synthesis algorithm. So the idea is to find contact points that allow a foreclosure grasp of an articulated object. The approach is conceptually simple because it is based on trivial kinematic knowledge that can be found in any textbook. So, and the approach can also search for a grasp for any predefined number of contacts, including redundant contacts. So the approach works well for any number of contacts on the object. And the goal is to search for contact points in a systematic way, assuming the links are described by point clouds and may have any shape. The normal direction at each point is known, and contact at each contact point can be either frictionless, allowing a normal force only, or frictional, allowing combination of forces inside the polyhedral convex cone that approximate the friction cone. The methodology we are following has three main steps. The first one is modeling the articulated object as a virtual serial robot. So we have the articulated object with n links, and we will add 6 joints to this real object in order to generate or to model a virtual serial robot with n plus 5 links and joints. So we have the links, and from link -4 to link 0 are virtual links. They do not exist in reality. And from link 1 to n are the links of the real object. Something similar happened with the joints. From joint -5 to joint 0 are virtual joints. And from joint 1 to n-1 are the joints of the real object. And of course, the contact point will be located on the real object. Makes no sense to consider points of a part of the robot that does not exist in reality. And on this point, we will apply different forces. Second step of the approach is the obtention of a generalized range space associated to the joint space of the virtual robot, and map the grasping forces to this range space. So the force or torque is to be applied at the joints to counterbalance ranges produced by forces on points of the articulated object are computed in this way. This is very well known. It's just the Jacobian multiplying the range on the contact point produced at the contact point, and this will generate the corresponding torques or forces at the robot joints. And when we have several ranges acting on the articulated robot, so the total force or torque that have to be applied at the joints to counterbalance the ranges is just the summation of all the forces, the effect of all the forces applied on all the links of the real articulated object. So, and for the object to be mobile, it must be that this vector of torques at the joints of the robot have to be null. So, if now we have a perturbation produced on by a force of any link of the robot, it has to be counterbalanced by the range produced by forces applied on the contact points on the virtual robot. Actually, on the real links of the virtual robot. And we know, as we saw in the previous slide, how to model the perturbation and how to model the ranges applied by the fingers in the generalized range space of the robot joints. So in order to counterbalance any perturbation applied on the articulated object, the set of ranges that have to be applied by the fingers must be able to span all the n+5 dimensional joint space of the whole virtual robot. So in this way, the ranges applied by the fingers can counterbalance any perturbation on any of the links of the articulated object. So the effect is producing a forced closure grasp in the joint space of the virtual robots described here. The third step of the methodology is the search for the grasp in the generalized range space using procedures analogous to those for a single rigid object that are already published in the related literature. I will use a hypothetical 2 degrees of freedom example to be able to show graphically the procedure. So the first thing to be done is to generate a random grasp, which is a selection of grasping points. And for this, we can use specific heuristics if we want to optimize this first selection in some way, but it's not strictly necessary. So each of the selected points will have an associated range in the generalized range space, which has an actual dimension of n plus 5. And I am representing here a hypothetical 2-dimensional example. So in this case, the selected ranges are range 3, 1, 2, 1, and 1, 1, and the convex hull they produce that does not contain the origin of the range space. So it is not a foreclosure grasp. Second step is that if it is not a foreclosure grasp, then we select a contact to be removed. And this is done by selecting a range in the range space that belongs to edges or hyperplanes of the convex hull that do not satisfy the foreclosure condition. This is that the origin of the range space is in the opposite side of this hyperplane with respect to the position of the convex hull. Once we have selected this point, we select another point that will replace this one. And this is done by looking for it in a region of the generalized range space determined by hyperplanes parallel to those that were previously used to select the point to be removed. So this determines a region. We choose randomly any range in this region, and we replace the preselected one. So now we have another grasp, in this case composed by range 3, 1, 1, 1, and the range asterisk, like I show here. And the convex hull of these 3 ranges contains the origin of the range space. So this corresponds to a grasp that is actually foreclosure grasp. So if we obtain this, we just return the grasp. Otherwise, we go to step 2 and continue the iteration until we arrive to a foreclosure grasp. So other than this algorithm, some other algorithms can be applied also in the range space. The second one is an algorithm for the grasp optimization. I will not enter into details. There's no time for it now. But the idea is that given a grasp, iteratively improve it until a local optimal grasp is obtained. So it's not just that it is foreclosure, but it is also locally optimal grasp. And by optimal, we mean that we are increasing the maximum range that the grasp can resist in any direction. This is in front of any perturbation on the articulated object. And another algorithm to be considered is the search of independent contact regions. So the idea is that given a grasp, the algorithm computes regions about the contact points of the grasp such that the contact on each of them maintain the grasp properties, and of course the foreclosure property. So let's see now some examples, 2 and 3D examples. Here we can see 2D examples, 2 polygons joined by a vertex. And here we can see the foreclosure grasp, and in the picture on the right, the optimal foreclosure grasp obtained after the optimization process. And here we just display the quality evolution during the iterations. This is another example with 3 links. These are of elliptical shape. And this is the foreclosure obtained in the first part of the approach. And this is the optimal grasp obtained after the optimization. So this is another example. Previous one was frictionless. This is frictional example, a frictional example. So here we are showing the initial random grasp, which is not foreclosure, of course. This link can be moved in this direction. So, and below we have the same articulated object with the contact points that produce a foreclosure grasp, and also the regions on the object surface that are independent contact regions. This is that the contact can be moved anywhere inside the region, that the contact will remain as foreclosure grasp, and the quality eventually will be the same of the initial foreclosure grasp. And this is another example with 3 links. So, but this is the same idea. Let's go now to 3D examples. This is a simple 3 links object modeled with 1,500 triangles, and we look for frictionless grasps with 9 contacts. These are the initial random contact points of the grasp. The grasp is not foreclosure. There is no force component in the -x direction, so we cannot counterbalance perturbation along x direction. And this is the final foreclosure grasp obtained in 4 iterations after 6 seconds. Now we will show a frictional example using 7 contacts for the same articulated object. This is the no force closure grasp, random selected. Note that there is no force in -z. And this is the final foreclosure grasp obtained in 22 iterations in 86 seconds. This is not optimized because some other activities are done while we are computing this, like graphical representation of things like that. Let's go now to a more defined object. This is a 2-link object with with more than 9,000 triangles. It's a spanner. This is the friction coefficient, and we use 8 sides for the polyhedral convex cone to approximate the friction cone. So this is a grasp obtained with 5 contacts, 3 contacts on the first link and 2 contacts on the second link. And these are the corresponding independent contact regions. Here we can see a zoom just to show with more precision where the contact points are located in on each of the joint of the links. This is another example, in this case using 6 contacts on the object, and the result has 3 contact points on the first link and another 3 on the second link. And these are the independent contact regions for this grasp. Let's deal now with a more complex object. It has 5 links, and the number of triangles to model the object is 5,800, above this number. The same parameter for the friction considerations. So here we have a solution using 9 contacts. These are the contact points that produce the foreclosure grasp of the object, and these are the independent contact regions represented as the center of the triangles that belong to the independent contact regions. And this is another example. Note that in this example there are no contact points on the 3rd and 4th link. So the object is immobilized just with contact points on the 5th link and the first 2 links. And these are the corresponding independent contact regions. So as future work, we consider now 2 things. One is the automatically reduction of the number of contacts to the minimum possible. These tasks seem to be not quite difficult, working in the generalized range space. For instance, removing from the convex hull of the ranges, contact ranges, those that are redundant and allow the generation of a new complex hull with less vertices and still keeping the original range space inside the complex hull. And the other point is the use of the knowledge of the shape of the generalized ranges in each link to improve the search in some way or the result. I say we know the shape of these ranges because we know the Jacobian for each of the links of the articulated object. So we can determine the expression of each component of these generalized ranges, and maybe they are useful to optimize something in the whole procedure. It is not clear whether this information may be useful or not, but it is something to be investigated. And that's all from my side. Thank you for your attention, and also thanks to Noé Alvarado for the examples and to the Spanish government for the financial support. Thank you very much.